everyone. It is January 28th, 2025, and this is the libhal biweekly meeting. All right, so we just have a few things on the agenda. First things first, I haven't really finished up going over the new serial interface. I think I came up with some other things I want to consider for it, and I haven't made any progress on how I2C target. The first slide to really talk about would be consider using large language models for bit masks. A lot of students find making the bit masks really annoying, and I agree. There are SVD files that we could parse in order to get the mask information out. But there's also another solution, which is simply to just use a large language model. You put in your user manual. You basically tell it, hey, pull out the register information and all the bit masks, and then follow this code. You can give it an example of some libhal code, and it'll be able to give it back to you. There shouldn't be any real legal issues with taking this public document and then just feeding it through a large language model to get the results back. But do prefer using your own local models over stuff you can get online. But you do you. Obviously, when it comes to large language models and writing actual code, I do want to say that in general, you can use it to help yourself out, but it's still your code. You're still responsible for it, and you need to make sure that you reread what the large language model came up with and update it to fit accordingly. Now, up to the next one. So there's been this particular issue that's happened, or not issue, but like this particular thing that I had to teach people, and it's honestly just bad design on my part. So when your docs fail, so let's say you put out a PR and you fail to bring up a parameter that was in one of your functions, Doxygen will see that and will create a warning. We dump those warnings into a file, and then if the file is contains something, or basically if the Doxygen fails, because we fail on warnings, if it fails, what we end up doing is printing out the Doxygen fail logs. The problem is that the error X that you see is in the run Doxygen, but not in the read out any Doxygen warnings. Before, it would just look like a normal little check. So you wouldn't know to open that up to see it. So now I've done it such that you should see X's on both of these. I set up the CI such that like if you notice you don't see anything here, you can always go to the next one afterwards. So this will be a little more intuitive. And if Doxygen does succeed, it just simply skips the read out Doxygen warnings. So this should be a little more intuitive when it comes to people creating PRs, looking at looking at the docs and seeing if it failed and figuring out why it failed. All right, so there's something that I've been thinking about. I'm not sure if we'll actually make this change anywhere. I think maybe USB might be one of the situations where this would be really useful. But the idea would be maybe we could adopt span of spans for things, or span of byte span. So right now, let's consider like serial or maybe even I2C to some degree, although it gets a little weird when you have things like that. Actually, I2C would be fine. Rather than just having a span of bytes, why not have a span of span? So the reason why this would be useful is you could have, let's say you have some read-only memory sections that have some data that you want to send over the line. So you have some const data. That data is never going to change, you're never going to update it. You're just always going to send out, let's say, like a header every single time. Let's say in a lot of cases, you could either send out the header and then in another function call send out the body. And this is usually fine. Usually the delay between write operations should be quite minimal, especially because usually your CPU can operate much faster than your baud rate can switch signals. So this isn't too big of an issue. But maybe in some situations, you need to keep the communication as tight as possible. One example that I can think of, I don't know if this is actually a real problem. It's probably not actually a real problem, but it is something that I considered, is where in USB, we may have these things called descriptors, and basically they are bits of information we have to send back to the host, your computer, to tell it what we're capable of. And a lot of times, you need to kind of keep all that information like all compact into one big buffer, all sequential, so you can just send the beginning and the end. But some cases, like how we're doing our architecture, We may actually want to split things up into separate pieces and then fetch each piece as needed. And it would be nice if we didn't have to take all those different pieces and throw them into a buffer first. It would be nice if we could just say, here is our sequence of pieces, put them all together and concatenate them into whatever register buffers you have, and then shoot them off. I'm not sure if this will work for all USB peripherals or if this is even like universally useful, but I did notice that potentially some drivers may expect that if you're going to send data out to something else, that you're going to fill up all the data. You're going to, if you say that you have a buffer that can, the peripheral says that it can push out 64 bytes each time, it may not make sense to push out 4, then 2, then 3, or then 1, and then 15 in separate steps. Getting all of the data all at once could be useful. So an example here would be, let's say you have some context per header, some payload. That's actually, the payload isn't context per. It's actually something that we get from the input. Then we have CRC doesn't even seem like a good idea. Maybe just a footer. These two parts are constants, and then we have a payload. Rather than having a separate write header, write payload, write CRC, which might have some delays between them, we could give them all three, and then it'll send those off. Just an idea. Might pop up in situations where it's necessary, but I think for now we can probably just stick with the normal span of bytes. And our little last slide of today, we're going to go over the device manager classes and kind of how they work. Before we would write a driver, that driver would implement some bit of hardware, and it was up to you to make sure that if you created a PWM class, let's say for the STM, that uses timer2, and you created a timer, to schedule events, and you also use timer2, those would be in conflict with each other. I think I said timer2. Yeah, timer2 in both cases. Those would be in conflict. What would happen is that you have now two separate drivers that are trying to control the registers in their own specific way, and they will step on each other. And this could end up resulting in pretty much undefined behavior. It depends on which one does what things at what time. Basically, it's a huge issue. And before my policy was, use the resources that you know to use. It's up to you to ensure that you don't mess up, you don't shoot yourself in the foot. This started to change when I started thinking about things like CAN, where this particular driver has this one resource where there are a lot of them, but then there are other implementations that have very few of them. And because it's so broad and wide, it kind of made it kind of confusing. I then realized that I think the best option in terms of how we manage our resources is actually to manage our resources and to actually symbolically represent ownership over a particular peripheral. I'll actually explain where this kind of ends though, but let's look at the CAN peripheral manager. We also looked at this last time we met. But notice that this class does not inherit or implement any interface. It does not implement CAN bus manager. It doesn't implement transceiver, none of these. All it does is simply hold the state and control over the CAN peripheral. There is one on the STM, and it just manages the entire object. Now, what you can get from it is a transceiver, a bus manager, an acquire object, an interrupt, a CAN interrupt, as well as also identifier filters and mask filters, and a whole bunch of other types of filters. This particular class manages what resources it gives to you, such as the identifiers, and if you run out of those identifiers, if there's no more registers that are available for you to acquire yet another identifier, it'll throw an exception for you. So this is to ensure that you never get in a spot. The code will literally stop you if you try to ask for more of the resources than you have available to you. You also don't get an opportunity, you don't get as much control over which particular filter you get. You can get filter 1 or 5. In this case, in your design, in most applications, especially for this peripheral where there's no real priority between them, it doesn't really matter. I might be wrong on that actually. There might be priority depending on which number you have, but I think in most applications it should not matter. Um, if there was a concern of priority, then it might mean that your masks and your identifiers are a little too they intersect. But even then, it wouldn't matter. You would still be able to receive the message regardless. But this idea of throwing an exception if you ask for more than you should, I think really lends itself well, in my opinion. I think that this is the right way forward. Um, and I think we're going to start doing this for everything else. So I'm going to give another example. I don't have it as a slide, but the STM timer. The STM timers can do a number of things. They can be timers, HAL timers, which means that you can schedule events with them. They will time out a certain amount of time, and then when that time elapses, it'll assert an interrupt, and that interrupt will then call your function, and then you can do the stuff from there. You can also use timers to create PWM signals, which is useful to generate PWM. So it implements PWM as well. And you can also use them as pulse capture. And there are a lot of other interesting and cool things you can do with them. You can even just use them as as a steady clock. Yeah, I mean, obviously, you can use them just to tell time. So rather than having each one of these be separate and then you give some information to each one of these objects to tell them, hey, you're going to look over, you're going to use timer 2 peripheral as your thing. No, what we're actually going to have is a timer 2 to 16 or basic timer class. And from basic timer, you can extract out a PWM that works for the basic timer. With the advanced timer, you can then extract out an advanced PWM timer. I'm sorry, an advanced PWM, which is just a normal PWM. We don't have advanced PWM. But that's pretty much the idea, is that we represent the managers, the peripheral managers, and the device managers in general manage the resources of a thing. Another example, right before we finish up for today, is I forget the name of the part. I believe it's the TCA. Basically, it can be an input, an output, an interrupt pin, and an ADC. It has a certain number of resources for all of these, but you can change any one of its output pins of its 8 channels to any one of those things. I think it actually only has up to 4 ADCs. I forget. But basically, when you create the TLA object, you get ownership and control over the TLA with that specific address. From there, if there is the UB of having 2 separate objects that both point to the same device, that would be complete chaos. I don't know if we're going to have any sort of way to detect that yet. But maybe as time goes on, we will make those changes necessary. But the idea here is that you have one object to own over the control over a very specific bit of hardware. And you can ask for resources that we know that hardware can actually give you and to manage those things. That way, I believe that the code will be a lot safer to work with, and I think that it'll be a lot easier to have a single object or single owning object that allows you to get back specific resources from things. Oh, and last thing I'll say, because I think it would bear saying before when I talked to some other students today, these all have lifetimes. So if, let's say you had an identifier filter set and you created like 3 of them, and then or created 2 of them and then you made another one that's inside of a different scope, and that scope goes away. The identifier that went away now is a resource that's been released. So the CAN peripheral manager should do, which it may not do currently. Actually, no, I think it does do this actually currently. What it'll do is it will look for any currently freed identifier registers. If it finds the resource that fits it, it will acquire it and then return it back to you. So the idea here is that if you do end up having one of your objects get destroyed, it frees the resource so that you could then call it again. But if you call it again and the thing's resources is basically taken up, has been acquired already, then it might throw an exception. But it also depends on what the device manager is built for. It depends on what resources the hardware has, and it's up to the documentation to explain to you, or the developer of the library to put in the documentation what the limits of any one of these calls are. And yeah, that's pretty much about it. I'll see you guys in 2 more weeks.